Alright, my dear children of class 11 science, we will do now a very important terms and even the relation that we are going to derive related to this wave. Okay, and this concept is important for class 12 also. Okay, as far as the wave topic is concerned, and the topic that we are going to do is called phase difference and path difference. Phase difference and path difference, and especially we derive their relation. That means the relation between phase difference, which is marked by letter delta phi, and path difference, which is marked by letter delta x. Now, to understand this and to derive the relation first, so as you know, you have already read that when a particle oscillates, when a particle oscillates, then the displacement of the particle from the mean position is also called equilibrium position, okay, and its direction of motion of the particle changes periodically. Means when a wave propagates, okay, in a medium, okay, then every particle medium displaces, okay, from its equilibrium position, so that due to that the position and the direction of motion of particles, different particles in the medium, changes periodically. Okay, it changes periodically or regularly. So under this case, we can always measure the quantity at any instant of time which determine the position and the direction of motion of particles, the displacement of particle. And this particular term is called phase. So children, for the propagation of wave, the position which is expressed by the displacement of and the direction of motion of any particle of a medium at any instant is expressed by the term called the phase of the particle. That means this term phase actually indicates the position and the direction of displacement of the particle of a medium at any instant time. So children, under wave propagation, okay, through a medium, remember this, all the particles of the medium oscillates in the similar manner about their position, mean position. So if we observe a few particles close to each other, we shall find that there is a displacement and a direction of motion of particle, and this displacement and direction of motion of few particles which are very close to each other are even different. They are different. So the difference in the angle of position and the direction of motion of particle is expressed by the difference in the angle between the particles, and this difference in angle is expressed by the term called phase difference. What difference? Phase difference. And even the difference in the distance of the particle, okay, in a medium with respect to each other is also expressed by the term known as path difference. So these are the two terms that we can measure and can express with each other when a wave propagates in a medium in any of the direction. So for that, let me just consider a wave which propagates in a medium, and yes, we are already in the wave which we are dealing with, that is called progressive simple harmonic wave. So I consider, suppose a progressive simple harmonic wave propagates. So I write down, suppose a simple let me use this word also, simple harmonic, okay, simple harmonic progressive wave. Simple harmonic progressive waves, okay, wave is suppose traveling. This wave is traveling in a medium. It's traveling in a medium, okay, in say a positive x-axis. Traveling in a medium, say positive x-axis. So if it is moving along positive x-axis, then we have done already, children, that the displacement of the particle. We have already done this relation, children, the displacement of a medium particle, any medium particle, the displacement of medium particle, okay, at a distance. At what distance? At a distance x from the origin. Distance x from the origin, okay, is given by y equals to a sine 2 pi. Okay, let me write this displacement. Actually, you have learned three different expression of displacement equation, but let me write one of the equation of displacement equation of medium particle at any some time, but at a distance x from the origin, and that is y equals to a sine 2 pi bracket t by capital T minus x by lambda. So this relation which I have written is in terms of time period, wavelength, and definitely the distance in which the particle have a displacement, okay, after a time interval in which the particle passes from the origin. Now in this equation, if you see, the sign is expressed by this quantity. So this is an angle. This is a what? Angle. And this is the phase of the particle. This is the phase of the particle in position x at any instant of time what? T. So in this relation, you see, in the above relation, if you see, this particular factor, that is 2 pi t minus capital T minus x by lambda. So this is actually the phase of a particle. This is the phase of a particle, okay, in position what? What position? Where the particle is at x, position x, at any instant of time, at any instant of time, and that time we have already considered is what? T. Okay, and this phase, as I said, is always expressed by the angle. So phase is the term which is always expressed and measured in terms of what? Angle, and we mark by symbol what? Phi. So this is a phase. So phase is expressed by symbol phi, and this phase of a particle is given by now is 2 pi t by capital T minus x by what? Lambda. So this is the phase. Now suppose at any instant of time t, there are the two phases. There are the two particles. Let me just consider there are the two particles which has a different phase. Okay, which means whose distance from the origin are different. Means the time interval is same, but they are the two different particles, okay, from the origin, and they are also at different distances from the origin, and they also acquire a phase, and that phase is expressed in a similar manner. So under this particular case, where there are two different particles which are at a distance, say x1 and x2 from the origin, at any instant time t, but they also have different phases, and that phases are say phi 1 and what? Phi 2. So if these are the different phases, then I can write the phase acquired by each particle at a distance x1 and x2. So phi following the same relation. So I write on phi 1. This is the phase of first particle, which is equal to 2 pi, time interval is t, capital T, minus x will be x1, and wavelength is lambda. And the wavelength and the time period is same for these two particles, because these particles are executing a what type of wave motion? A simple harmonic progressive wave. So the time period and the wavelength remain what? Same. Okay, so this is the phase of the particle. Similarly, I write on phi 2. So phi 2 equals to 2 pi small t by capital T minus x2 by what? Lambda. So this is the phase of the second particle. Now what I do, this phase which are acquired by the different particles. Now what I do, I take the difference of this phase, and this difference in the phase between the two particles is actually measured by the what term? Phase difference. But children, let me just tell you that since if I write x2 is greater than x1, that means if the phase of the second particle is greater than the phase of the which particle? First particle. Okay, then in this case, the phase difference between the two particles now can be measured as phi 1 minus phi 2. And this phi 1 can be replaced by say 2 pi bracket t by capital T minus x1 by x2, x1 by lambda, minus this phi 2 means 2 pi bracket t by capital T minus x2 by lambda. Now we take common. Now we'll take common and open the bracket. The expression can be now written as 2 pi. Okay, now you can see the common, I can say take out is 2 pi bracket. Okay, so inside the bracket, let me just write down phi 1 means t by capital T minus x1 by lambda. Okay, minus now I'll take common. I've taken the common 2 pi, so it will be t by capital T. Now minus become plus, it will be x2 by lambda. So I have taken common from both the expression. Okay, so that 2 pi is common, so t by capital T minus t by capital T will cancel out. So now you can see what will remain, 2 pi. Now plus x2 by lambda is remaining, so I write down x2 by lambda first, minus then what is remaining? x1 minus lambda. So that means phi 1 minus phi 2 equals to 2 pi x2 by lambda minus x1 by lambda. But still you can see what is common. You can take common lambda also. So lambda in the denominator, if I take common, so inside the bracket, this x2 minus what? x1. So phi 1 minus what? Phi 2. So phi 1 minus phi 2 equals to 2 pi by lambda bracket x2 minus what? x1. Now this phi 1 minus phi 2 is expressed by delta phi, and this delta phi is the phase difference with corresponding to 2 pi by lambda and this x2 minus x1 is the difference in the position of the particle from the mean position, and this is actually called as path difference, and we express by letter delta x. So if you look at the relation, children, delta phi, I write on where delta phi is the what difference? It is the phase difference. Delta phi is the phase difference, and delta x is the what difference? Path difference. So when a wave propagates in a medium, so all the medium particles vibrate in a different manner. Okay, but between any two particles we can measure the phase difference and path difference. So the phase difference for the wave which propagates in a medium is expressed by 2 pi by lambda into what? Delta x, and this is equals to what difference? Path difference. Okay, now as you know, if two particles, if they have a path difference, that equals to lambda, and lambda is also the wavelength of the wave. Okay, that means if equals to wavelength, if the path difference is equal to the wavelength of a wave, then your phase difference will be equals to delta phi equals to what? 2 pi by lambda into lambda. So I replace delta x by lambda, so this lambda cancel out, which means delta phi equals to 2 pi. So your phase difference will be 2 pi when the path difference is what? Lambda. Thus the phase difference between two medium particles having path difference lambda is always has a phase difference what?